All right, welcome back. In this addition to the CBS conflict-based search video, I want to talk about something called disjoint splitting, which is a really interesting paper that essentially follows CBS and augments it to improve things further. So here I want to have a look at something called disjoint splitting. So I'm using the same example as we've just seen from the conflict-based search video, and we have these three conflicts. Essentially, we saw that every time we look at the left side of the tree, that is the version where essentially agent 1 is not allowed to be at the location, right? So the pink agent has to do some form of waiting for one time step. And then the right-hand side of the tree kind of followed the idea that the green agent, agent 2, kept trying for 3 times to plan a different path, and then eventually learned down here that it too also has to wait, right? So what I want to show you is that by another reframing of the idea, we can really improve the performance of this algorithm CBS simply by choosing a smarter way of how we actually represent splitting, and I guess technically also how we are conducting the splitting. So these ideas, this idea of this disjoint splitting, I think this is again really borrowing ideas from the constraint programming CP optimization field as well, and kind of applying it back across, which is really an exciting cross-pollination. So really this is actually just we're going to be doing the same thing, right? The underlying algorithm doesn't change per se. So this is still 9 and this is still 8, but we'll see actually what's going to happen is we're simply rephrasing the way we write constraints. So I'm going to copy across on the left-hand subtree here. This is going to be the same. I'm going to write this slightly differently this time, so 1, D2, 3. One way to write this logical not as well is to similarly kind of show the bar on top. So this bar on top means not as well. I'm just doing this because it'll be easier to distinguish the two sides. Now let's talk about the underlying intuitions here. What's actually happening, as I just described, we almost have this left-hand side of the tree, which is representing very similar worldviews. And then there's also the right-hand side of this tree, which is very different worldviews, right? Where you're trying different paths. Now, the right-hand side makes sense, right? We're going to have to explore this because things keep changing. These are different possible paths. But the left-hand side is actually really important. If we have a think about this, what did this plan actually correspond to, right? So we're saying agent 1 is not allowed to be at the location, so it has to do some form of waiting move at some point in time. Let's say, based on tie breaking, it did the waiting move at its origin, right at the beginning, okay? It's the hand-wavy way, but it will make the most sense for visually demonstrating why this is important. Okay, so this path, it waited once at the time step, then went across to its goal. Right, that is a symmetrically equivalent path. That's a cost of 5. If we continue down, well, this is the path where the green agent is doing this, right, down the middle in the C column. And here, again, we know that the pink agent, agent 1, had to wait one time step. Well, if it waits at the beginning, that's the exact same path. Okay. If we did it again, you would see that this as well is also the same version of the path where agent 1 is just waiting at some location. Let's say it was also at the origin. So what we're seeing, interestingly enough, right, is that essentially in this, when we're not thinking about our splitting, right, and we're just doing the basic splitting that CBS was originally written in terms of, where you add in a harsh constraint. Not this, not that. Well, what ends up happening is we actually see that we're encountering the same world state, really, in different subtrees, right? You have almost this problem of redundant symmetry, yeah? So the same subtree is showing up again and again and again and again. And the beauty is that through a subtle reframing of the problem, using something called disjoint splitting, we're going to be able to completely avoid this problem, or at least substantially reduce this problem in these cases. So what we actually do instead is we are going to swap our viewpoint. How are we doing this? Well, what we're doing is on the left hand of the tree, on one of the splits, it will be this agent is not allowed to be here, right? It's the negative split. The right hand, we're going to do the opposite. What we're going to do is actually enforce that one of the agents has to be at a location. That's interesting, right? So a reframing of the problem, which kind of is like almost symmetric in meaning, we'll see that it has a surprising result. So that's why I use the bar, because this version is saying, hey, this one, agent 1 is not allowed to be at D2 at time step 3. Here, I'm going to write it again in terms of agent 1, but I'm saying that agent 1 has to be at location D2 at time step 3. Okay, so this is the idea of disjoint splitting. I'm enforcing then that the pink agent does have to go its straight path. It has to be there. This is the same worldview, I guess, right, between these two states. This actually didn't change the path that would be happening. So that's interesting enough. But what does this do then? We'll still identify, of course, that we have these collisions and we split, but now see what happens. So on the left side, what is our constraint? Well, we say here that we had, again, the same constraint. Okay, can you see what actually happens here, though? Because what we've just said is agent 1 has to be at location D2. Okay, agent 1 has to be at location D2 at time step 3. So what that means is that this constraint here saying that agent 1 can't be at C2 at time step 2, well, this is invalid. This is actually not possible based on the previous constraint. What that means is actually this node here, not only, it's not like we're pruning it, it does not get generated because this was not a valid plan because of the way that we've changed our worldview and we've enforced that the agent has to be there. So then on the other side, we'll write it in the new terminology, right? So we're saying that agent 1 must be at location C2 at time step 2. Okay, so that is actually technically, again, the same cost path, and it kind of corresponds to the exact same path. And then you'd kind of continue, but you'd see that here, when I go to do this again, this is now a dot, dot, dot. Well, we would have again the constraint that 1 cannot be at B2 at time step 1. Well, once again, this is incompatible with the constraints we've already seen at a higher point in the tree. These follow through right to the entire subtree. You're essentially building up a series of constraints. So because of that, again, we don't even have to explore this. The other version is, again, 1 must be at B2 at 1, which is the same worldview. And finally, we get to the idea that even there, in that final node, the pink agent, agent 1, was going to have to wait 1 time step, has a cost of 9. And we would, of course, then expand in the same last node, number 9, right, where we learned that agent 1 has to wait, cost of 5 plus 4 equals 9. So this is still, right, complete and optimal. So disjoint splitting is this really super cool idea, such an easy reframe, right, of just the idea is we have one of the constraints be a negative constraint, one be a positive, right, like enforcing a location. And because of this, we're able to essentially prune for free, right, this idea of these symmetric subtrees that we otherwise would have just had in the search tree. We might have to expand these, right, and then you're even doing more and more heap operations and so forth. So these we just don't have to generate at all. We're massively increasing both the speed of the algorithm, right, because you're doing less operations, you have to do less search, you have to generate less nodes. And we're also increasing essentially the success rates of the algorithm subsequently because it's able to solve problems in a faster time, right, within whatever time limit is kind of given. So the original paper kind of says this simple disjoint splitting idea actually essentially doubles the speed and success rate of CBS. So anyway, that's disjoint splitting. So thanks for watching, and I'll see you in the next video.